Hi everyone, welcome to this tutorial on recursion in C programming. My name is Rainier Gonzalez Madayag, and today I'll be your instructor for this session. In this video, we will learn about what recursion is, how recursive function works, the two main parts of recursion, and some classic examples like factorial and Fibonacci. We're also going to talk about common mistakes and how to avoid them. By the end of this video, you should be able to confidently write and explain a basic and recursive function in C. This video is divided into three parts. First, the lecture or concept discussion. Second, the code demonstration and walkthrough. And third, common pitfalls and final tips. So, what are you waiting for? Let's go. Okay, so first, let's understand what recursion is. Recursion is a programming technique where a function calls itself in order to solve a problem. Instead of solving the entire problem at once, the function breaks it down into smaller versions of the same problem. In simpler words, a recursive function is a function that repeats itself but with smaller input each time. Now, every recursive function must have two important parts. Number one is the base case, and number two is the recursive case. Base case is the condition that stops the recursion. Without it, the function will keep calling itself forever, which will crash the program and cause a stack overflow. The recursive case is the part of the function where the function calls itself again with a modified value. So basically, here's a simplified real-life example for this. Imagine you are standing between two mirrors. You see your reflection repeating again and again. That's similar to how recursion works. It keeps repeating until it reaches a point where it stops. Another example is thinking of opening a set of nested boxes. You open one box and find another box inside it. You keep opening until you reach the smallest box. That smallest box is like the base case. Now, why do we use recursion? We use recursion because some problems are naturally repetitive and easier to solve using recursion than using loops. Examples including factorial, Fibonacci sequences, key structures, searching and sorting algorithms. However, recursion must be used carefully because it consumes more memory than loops. Now, let's move to our first example, which is the factorial of a number. The factorial of a number means multiplying that number by all positive numbers below it. For example, factorial of 5 is equals to 5 times 4 times 3 times 2 times 1. In recursion, we define factorial like this. Factorial of 0 is equals to 1. This is our base case. Factorial of any number greater than 0 is equals to that number multiplied by the factorial of the previous number. So if the user enters the function 5, it will work like this. Factorial of 5 equals factorial of 4. Factorial of 4 equals factorial of 3. Factorial of 3 equals factorial of 2. Factorial of 2 equals 4 factorial of 1. And factorial of 1 equals factorial of 0. Factorial of 0 returns 1 and stops the recursion. Then the values are returned back upwards and multiplied until the final answer is produced. Alright, now let's move on to the live demonstration of how recursion works using the factorial program. First, I already have my factorial program open in the C program is. This program uses a recursive function to compute the factorial of a number entered by the user. Before I run it, let me quickly remind you that the idea behind factorial, the factorial of a number means multiplying that number by all the positive numbers below it. For example, 5 factorials is 5 times 4 times 3, like I've said before. 3 times 2 times 1 is 120. Now I will run the program. You can now see the screen that the program is asking me to enter a number. I will enter the number 5, then press enter. Now, the program displays factorial of 5 is equals to 120. Now let's explain this step by step, how the program got this answer using recursion. When I entered 5, the program called the factorial function and passed the value 5 to it. When I entered 5, the program called the factorial function and passed the value 5 to it inside the function. The program first checked if the number is equal to 0. Since 5 is not 0, it did not stop yet. Instead, it went to the recursive case and called the same factorial function again, this time passing 4. Now, let's talk about another example, the Fibonacci sequence. The Fibonacci sequence is a series of numbers where the first two numbers are 0 and 1, and each next is the sum of the two previous numbers. So the sequence goes on 0, 1, 1, 2, 3, 5, 8, and so on. In recursion, Fibonacci of 0 returns 0, Fibonacci of 1 returns 1. These are our base cases. For any number greater than 1, Fibonacci of n is equals to Fibonacci of n minus 1 plus Fibonacci of n minus 2. Once again, the function keeps calling itself until it reaches the base case. Now, let's discuss how recursion really works inside a computer. Every time a function is called, it is stored in something called the call stack. Each recursive call is added to the stack. When the base case is reached, the stack starts to clear as each function finishes its execution and returns a value. This is why too much recursion can cause stack overflow, because the stack memory gets full. Alright, now let's move on to our next live demonstration. And this time we will use Fibonacci sequence to further understand how recursion works. As you can see on the screen, I have my Fibonacci program open in the editor, which is C Programmist. This program generates a Fibonacci sequence using a recursive function. Before I run the program, let's quickly recall again what the Fibonacci sequence is. The Fibonacci sequence starts with 0 and 1. After that, each number is the sum of the two previous numbers, so the sequence goes like 0, 1, 1, 2, 3, 5, 8, and so on. Now I will run the program. The program is now asking me to enter the number of terms. Let's say I enter the number 7, then press enter. The program now displays Fibonacci series 0, 1, 1, 2, 3, 5, 8. Now, let's explain step by step how this output was produced using recursion. When I entered 7, the program did not directly calculate the Fibonacci numbers right away. Instead, the for loop in the main function started running from 0 up to 6. For each value of I, the program called the Fibonacci function and passed I as the argument. First, the program called Fibonacci of 0 inside the function. The program checked the first condition if the number is equal to 0. Since it is 0, the function returned to 0 immediately. This is our first base case. Next, the program called Fibonacci of 1. This time, the first condition was false, but the second condition became true because the number is 1, so the function returned 1. This is our second base case. Now, when the program reached Fibonacci of 2, both base cases were false, so the program moved to the recursive cases. It returned to the Fibonacci of 1 plus Fibonacci of 0. From our earlier results, Fibonacci of 1 returned 1 and Fibonacci of 0 returned 0. When we add them, the result is 1, and that is why the third printed number is 1. Next, Fibonacci of 3 was computed by calling Fibonacci of 2 plus Fibonacci of 1. Fibonacci of 2 returned 1 and Fibonacci of 1 returned 1. 1 plus 1 is 2, so the next number printed is 2. Then Fibonacci of 4 called Fibonacci of 3 plus Fibonacci of 2. That became 2 plus 1, which is equals to 3. Fibonacci of 5 called Fibonacci of 4 plus Fibonacci of 3. That became 3 plus 2, which equals to 5. Finally, lastly, Fibonacci of 6 called Fibonacci of 5 plus Fibonacci of 4. That became 5 plus 3, which equals to 8. This is how the sequence 0, 1, 1, 2, 3, 5, and 8 was generated. What is important to notice here is that unlike the factorial example that only made one recursive of each time, call each time, the Fibonacci function makes 2 recursive calls for every number greater than 1. That means the number of generation function calls increases very quickly, which is why recursive Fibonacci becomes slow for large values. I'm sorry if it's dark right now, but we're now gonna tackle about like loops versus recursion. Loops repeat using conditions like for, while, or do while. Recursion repeats by calling the same function again. Both are powerful, but recursion is often more readable for problems that are naturally repeat in structures. Now, let's talk about some common mistakes students make when using recursion. Mistake number 1, no base case. If you forget the base case, the function will never stop calling itself. This causes infinite recursion and crashes the program. Mistake number 2, wrong base condition. Sometimes the base case is written incorrectly, so the function either stops too early or too late, producing wrong results. Mistakes number 3, using recursion when loops are better. Recursion is powerful, but not always efficient. If a problem can be solved easily with a loop, using a loop may be better in terms of memory usage. Mistake number 4, not understanding the flow of the function. Many students struggle because they don't visualize the function calls stack up. A good tip is to trace the function calls step by step on paper. Now, for the summarization, to recap today what we have learned, we have learned about what recursion is, the meaning of base case and recursive case, how recursion works using factorial and Fibonacci, how the call stack works, and the most common mistakes to avoid. For your next step, I encourage you to practice writing your own recursive programs, such as calculating powers of numbers, finding the sum of digits, printing numbers in reverse using recursion. The more you practice recursion, the easier it becomes. If you found this tutorial helpful, please like, share, and comment below. Don't forget to subscribe for more programming tutorials about recursions. Yeah, thank you for watching, and I'll see you in the next video. Bye.